All right, welcome back to Heinzel Vision. It's been a while. We are starting the next unit, which is a unit on circular motion, an introduction to circular motion. So let's start by going back through the year. And if you think back to the first semester and what we studied in terms of motion and mechanics, we looked at a lot of linear situations, things moving in a linear plane or in a linear path, or things moving in a two-dimensional manner like a projectile where the force was constant. So in circular motion, now we're going to look at things that are experiencing rotation, things that are moving in a circular manner. So if we think through some examples, we can start with amusement park or games. We have loops in a roller coaster, which is a vertical circular motion, the merry-go-round, which is a horizontal circular motion, or a roulette wheel where the ball spins and you have the table itself spinning the other direction. Those are all examples of circular motion. With terms of cars or in terms of machines we use, right? If you turn left or right, you experience a circular motion. We're going to try to explain why your body feels the forces it does when your car turns left and you feel kind of a pull to one side or the other. Bank turns as well. If you think about a NASCAR track or a race car track, they're going to have turns that are banked inwards as they go in a circular path, and there's a reason for that. So we'll look at some problems like that. And fans are another thing that we use often in the summertime, especially that undergo a circular rotational motion. If we go to nature for some examples, a tornado, right? A tornado rotates around, as well as if we take a look at the sky. Well, let's start with the Earth, right? The Earth rotates on its axis, and the Earth also rotates in a circular manner around the Sun in orbit, just like the Moon rotates around the Earth. So there's a lot of circular motion when we talk about things out in space, out beyond our home here on Earth. And then finally, some examples from the world of sports. Throwing a baseball. As you arc that baseball over your head before you release it, you are undergoing a circular path. And then the hammer throw is a really good example from track and field. The hammer throw being the object mass on the end of a cable that you spin around and spin around and spin around and then let go. So that's a very good example of circular motion that's often used in example problems. So you can see there's a wide range of applications for things moving in a circular path. So let's start with some of the basics. Let's just use this example of, let's say this is a ball on the end of a string of a certain radius, and that ball is being rotated in a circular manner. Some of the things we want to know right off the bat is how fast is the ball moving? So if I took a snapshot of the ball at any point in time, we would say it's moving in the direction of the circle at that time, which we call its tangential velocity. Now, as it rotates around to other spots in its circular path, that velocity changes direction, right? But we know the direction that it's pointing at any given time is tangent to the circle based on taking a small view of that circular path. If you focus in on that, in that instant, it's moving in that direction. So tangential velocity is important, but it's easier to deal in terms of speed, rotational speed, or how fast is the object moving on average as it goes around in its circular path. So let's define its speed. Now I'm not going to vector it. I will just say average, v average. That's my speed. Linear speed, to be specific, because we'll have to differentiate between linear speed and rotational speed as we move forward in this unit. But so it's linear speed. It's just how fast is that ball moving on average as it goes in its circular path. So how can we determine that? Well, we would need to know a couple things about the object. If we knew the distance it traveled, right? So how far does it travel around the path in a circle? Essentially, I'm looking at its circumference as we go around. So we can call that delta S, S being my arc length, right? Just as a general term. S will be arc length in this unit, divided by the change in time, right? Or how much time went by for it to carve out a certain path. But if we look at a full rotation, a 360-degree rotation, we can use some properties of circles that we know already to come up with this formula in a specific manner. That is, if I know the period of rotation, so the time for one full revolution, or 360 degrees of revolution, we call that capital T, the period. So the period is the time for one full revolution. And the distance, the arc length that's traveled in one period is just one circumference, which is pi times diameter, or since we often deal with radius, 2 pi times the radius. So the first relationship we'll use is that average speed, linear speed of something moving in a circular manner, is 2 pi times the radius divided by the period. Now in the next couple videos we'll begin to look at velocity, and because the velocity is changing direction, we're going to have to deal with it in a slightly different manner and look at its acceleration in terms of its changing angle. So we won't get to that yet. Let's just stick with linear speed of something moving in circular motion, 2 pi r over t. Now you'll notice we're using r. We're also going to be using theta a lot. We're going to be referring to things in a circular motion in terms of polar coordinates often because it's easier. If we're using x and y's, we're constantly then transforming things that have a constant radius into x and y. You're doing a lot more trig, so it's very convenient when we're talking about rotational motion to refer to things in terms of polar coordinates. Or it's r, it's radius away from the origin, and the angle over which it's displaced. So let's define a couple things that you've learned at some point in math class, hopefully, regarding polar coordinates. So what are polar coordinates? Polar coordinates are r and theta as my two degrees of freedom defining a position in a plane, and s is going to be my arc length, so r is my radius. One thing we do with polar coordinates is we use radians, which is my SI unit for an angle. So we're going to be going away from degrees and into radians. Well, what is a radian? Radian is essentially just the ratio of the arc length to the radius of something moving in a circular path. So let's say I were to rotate 360 degrees around a circle, and I want to know how many radians it is. Well, if I take a 360 degree path, right, I will have gone one circumference, which is 2 pi times r, and if I divide that by the radius, right, the ratio there tells me that 360 degrees is 2 pi radians. Okay, so this is where we can get the basic relationship between degrees and radians. Well, what about 1 radian? What's 1 radian? Well, 1 radian is when s over r equals 1, right? Then I've rotated 1 radian. Well, at what angle in degrees do I rotate where s and r are the same? Well, I can find that from this ratio. If I divide both sides by 2 pi, right, I get that 1 radian is 360 degrees divided by 2 pi, or 57.3 degrees. Okay, so these are some helpful relationships when you're transferring back and forth from degrees to radians, since we'll use radians. We can also rewrite this. If I know the radius of my circle and I know the angle that I displace in radians, I can find the arc length by rewriting this equation, s equals r times theta. Okay, so that's it for the intro. So average speed in circular motion, examples, and then knowing how to use radians, how arc length relates to the radius in theta. In the next video we'll start to look at now angular velocity and how is that related to tangential velocity and the polar coordinates that we've derived.